Okay, so what we want to do now is look at this period derivative diagram and give us some idea about why we might want to find certain pulsars in certain areas of this period derivative diagram to help us better understand the population or use them as probes or something like that. So let's have a look at this. So if we first zoom in on this region at the bottom left-hand side, the so-called millisecond pulsars, why is it that we would like to find more millisecond pulsars, for example? Well, one of these ideas or reasons why we want to find more millisecond pulsars is we want to use them to try and detect gravitational waves. Now, you may be familiar with the fact that gravitational waves have been detected using LIGO and Virgo, and these instruments are finding systems which correspond to black holes merging or neutron stars merging, or even we've just recently been hearing about lots of discoveries of black hole neutron star mergers. And so we think that these events are for objects that are sort of anywhere from a few 1 to 30 or 40 solar masses. What we want to do with pulsars is we want to detect gravitational waves from supermassive black holes. So the sorts of black holes that are located in the centers of galaxies. And we expect that these should merge. So how does this work? Well, what happens is that when a gravitational wave passes over the Earth, it changes space-time around the Earth, and the apparent distance to our pulsar changes by a small amount. So we've shown it here as a delta L. It turns out that, as you can imagine, if the gravitational wave passes over the pulsar, it also causes a change. But in this case, we're only interested in what happens to the Earth because that is a correlated signal to all different pulsars. And the sort of frequencies we're trying to detect gravitational waves at are so-called nanohertz frequencies. This corresponds to periods of a year or longer. Okay, so we're talking about very long wavelength gravitational waves is what we're trying to detect with pulsars. So here is a bit of a graphic to show you what that looks like. So we have the Earth down here at the bottom. We have two pulsars for an example, and a binary supermassive black hole. And none of this is to scale, by the way. Of course, these binary supermassive black holes are located many millions to billions of parsecs away. And so what we expect to happen is that as the gravitational wave passes over the Earth, as I said, we expect to see a change in the arrival time of the pulses from these pulsars. And depending on the angles to them, we expect a certain degree of correlation in the changes that we see. And you can compare this to, say, the Virgo gravitational wave detector on Earth, where here now these are the arms of the gravitational wave detector. And in this case, they fire laser beams up and down these evacuated tubes. But in our case, we use the radio waves from the pulsar to make our gravitational wave detector. And here is a little video that shows you an example of what we might think is going on in these systems. Now, of course, these are two galaxies are merging together. We believe that the vast majority of galaxies have supermassive black holes at their center. And what happens is that as the galaxies merge, we can see that the green lines here represent space-time. Of course, you know, it's only in 3 dimensions here, but the motion of these galaxies around each other causes the emission of gravitational waves. These gravitational waves travel from those merging galaxies all the way into our galaxy. And here they pass over the Earth. And you can see here the color of the signal from the pulsar changing, indicating that the arrival time is changing as the gravitational wave passes over the Earth. Okay, and so we expect these very, very small changes to be able to be measured using pulsars. And in particular, well, so why is this interesting? Sorry, let me just touch on that first. Why is this interesting? Well, one of the main reasons it's interesting is we want to understand how the structure that we see in the universe formed. So how did we get all of the galaxies, the clusters of galaxies, and all of the structure that we see? And there are two different scenarios which you can imagine. One is called top-down formation. So if time is moving down the page here, we think that we have the early universe, then there are superclusters were formed first, clusters were formed after that, and then galaxies and then stars. The so-called bottom-up formation says that we have gas clouds, stars, and galaxies first, then galaxies form clusters, and clusters form superclusters. Okay, so these are the two different mechanisms which you can imagine for how we get where the universe to look like it does today. And if we have the so-called bottom-up, which is the favored mechanism, what we think happens is these are perhaps we'll just concentrate on the right-hand side here. Is that we start off with these so-called some massive stars here, and we start off with direct collapse of material to form these to form these so-called proto-galaxies here, and then we end up these massive stars explode, and we get massive black holes, and then these black holes we start to attract more material. They will merge, and then eventually, slowly but surely, we end up with all galaxies with greater than 10 to the 10 solar masses contain supermassive black holes. Okay, and so depending on the exact mechanism by which this happens, we expect that anywhere between 60% and 100% of these galaxies might contain supermassive black holes. And so this whole process means that there must be lots of merging supermassive black holes, because we need to grow the black hole, right? We don't think that we get 10 to the 9 solar mass black holes just like that. They actually grow through the merging process. And so this merging process should give off gravitational waves. And so we can use the pulsars to study that. So that's a very active area of research right now. And the reason we need more pulsars is that we need to look in many, many directions to try and measure this correlated effect that we expect from many, many thousands potentially of these merging events going on. So where else might we want to search for pulsars? Well, again, let's take a look now at these young pulsars. So we've looked at the millisecond pulsars already. What about these young pulsars? Why might we want to look at the young pulsars? Well, we can look at the exotic physics of neutron star interiors. So remember, I told you about the fact that the density of these objects is such that 1 teaspoonful of the material weighs around about the same as 1 billion elephants. So what does that mean in terms of what we think the neutron star is made up of? Well, here's a cartoon of a cut through of a neutron star. We can see that we have densities, incredibly high densities, 4 times 10 to the 11 grams per centimeter cubed here in the so-called outer crust region. So we have the atmosphere that I briefly mentioned earlier. Then we have an outer crust, which we think is like a lattice, a bit like a crystal. So you know, you might be familiar with crystals, and this is what we think this structure might look like, some sort of lattice here. And then we get the inner crust, and then the density gets even higher here, something like 10 to the 14 grams per centimeter cubed. And this starts to distort things. So we get these so-called puster phases. Okay, so these look a little bit like puster shapes. So we get deformed nuclei, and we might get sheets formed. And as we move down through the neutron star, the nuclei get more neutron rich. Okay, so we're getting less and less protons and electrons. And then when we get into the center, that's when things start to get quite weird, perhaps. So we end up with these individual protons, but we also get neutrons in the outer core region, and that's about 95%. So in the outer core, we expect around 95% neutrons. And then if we get right into this inner core region, it's really unclear what we get. We might get quarks, we might get free quarks, we might get strange baryons. There might be all sorts of different exotic material in there. And so understanding this interior structure of these neutron stars allows us to probe physics, which we just could not even contemplate simulating here on Earth. So the millisecond pulsars provide us with an opportunity of getting the mass and perhaps the radius, but more the mass of the neutron stars. So for every single model, that we have of what these neutron stars look like, we can make a so-called equation of state. And that's one of these curves that's shown here as these lines. Okay, so these indicate how the mass will change with radius for these objects. And so what we need to do is we need to find pulsars that can constrain this. Okay, and so the fastest pulsar that we know about has a rotation period of 716 hertz. And so that gives us a line in this plot which says that at the surface, we can't travel faster than the speed of light, of course. And so that gives us a line in this curve that says, okay, for this mass and this radius, we expect this to be the line. If we were to find a pulsar which had a spin period of twice as fast as that, it would already be incredibly constraining in terms of ruling out quite a lot of these different equations of state. Okay, and so finding faster and faster spinning pulsars is incredibly useful to measure the equation of state of the complicated material in the center. And here, just indicating again, just the fastest pulsar that we know about right now gives us this line here. We can also try and measure the masses of the neutron stars, and that can be done in a number of different ways. We can use gravitational effects like Shapiro delay, or we can, if we're lucky enough that we can discover the companion star in a binary system, if it's not another neutron star, we can maybe therefore measure the mass of the companion and therefore get the mass of the pulsar. And here's just a graph showing all the, apologies for that, all the different masses of neutron stars that have been measured so far. And what's constraining for these equations of state is the more massive neutron stars. So the more massive we find a neutron star to be, the more constraining it will be for these equations of state. So if you take again the equation of state diagram that I showed you before, if we now put a mass, so if we say that the most massive neutron star we've measured has a mass of 2.2 solar masses, it says that only these models up here are still valid in terms of equations of state, because none of these other models can make neutron stars that are that heavy. So I hope to have given you a brief overview of what pulsars are, why they're interesting, and why we need to go and discover more of them. And the way forward to discovering more of them is the building of the Square Kilometre Array. So the Square Kilometre Array is 2 telescopes, in fact, one in South Africa, and ultimately will be distributed throughout Southern Africa. So in phase 2, it will extend to other countries within Southern Africa. And then the other is located in Australia. You can see on the left-hand side, there'll be these so-called dishes in South Africa. They will operate at frequencies of 350 megahertz and above. And then below 350 megahertz, we'll use these so-called dipole antennas, located in Western Australia. And you can see that in both cases, they're located in very remote regions. And this is so that we get as far as possible away from human activity, which can generate radio interference. So what do we expect that we'll be able to do with these? Just skip over that. So we'll do pulsar surveys with both telescopes. And the important thing is that we expect that with the mid telescope, we'll be able to find anywhere between 6,000 and 9,000 new pulsars and 700 to 900 millisecond pulsars. And with low, we'll be able to find about half those numbers. There could be up to 100 so-called relativistic binaries. So these are these binaries that are moving very, very fast that we can use for gravity tests. We'll also be able to find pulsars in the galactic center. And we'll also be able to find pulsars in other galaxies further away than the Large Magellanic Clouds. So it's expected we'll be able to find a huge number of pulsars to add to our pulsar population. So just in conclusion, pulsars are these incredibly exotic objects. They are interesting in their own right because of the extremes of physics that they can allow us to probe, but they also are very useful for testing theories of gravity, exotic matter, and all sorts of other interesting physics. I hope you've enjoyed this, this tour of pulsars. You may want to go back and watch some of these videos again, as I know we've covered a lot of material in just a couple of hours. If you have any questions, please don't hesitate to get in touch with me. I hope you've enjoyed this, and I'm happy to answer any questions.